To the AI Guild podcast. When a human sees another human, they possess a wealth of information on how that body might exist within our physical world. When a machine sees a human in that same pose, the machine does not understand the pose and its implications. For example, the machine doesn't know that my elbow bends inwards instead of outwards. For future robots interacting with humans, especially any robots that would be physically touching a human, it would be incredibly important for it to understand the ways in which I can and cannot bend. This episode, we speak to Christoph Lassner, who worked on extracting a 3D model of a human pose and shape based on a single photo. We'll show a few examples of what this looks like and how it works in the show. Christoph, thanks for being on the show.
Thank you for the invitation. Glad to be here.
Yeah, so I would love to know, what were you working on that triggered this research?
So actually, the real cause for that brought me into the field was actually really switching to Tübingen, to Michael Black's group, where people have been working on body models for quite a while. So for me personally, it was joining the group, especially for getting into these 3D body models, because it's also pretty new still. The community is not yet working on 3D body models on large scale, especially when it comes to fitting them to 2D images, because classically we're still working on key point detection. So finding the key points of the human skeleton, finding them in 2D, bringing them to 3D, but dealing with the 3D bodies is not so easy. And Michael had set this up here very, very nicely. And we do have a 4D scanner here, which basically enables us to capture a lot of 3D scans with a very high timely resolution, so that you can get body movement in a very, very detailed way. And then you can build on top of that to go to a detailed body model. And so we had these facilities here. And then at some point we thought, okay, it would be really nice to see how we can do this with the single images. And then Federica and Andrew, who were actually the first authors on this paper that we're discussing, led a very, very nice way into this direction. And that's how it came.
Cool. So you said a 4D kind of environment to kind of model people. So is that just kind of, you put the little kind of nodes on each one of your joints and you're kind of walking around and there's multiple cameras and you're kind of like, this is probably a terrible example, but I picture them filming Avatar. Is it like that type of concept?
Oh, for luck, it's even more detailed, right? So for the classical motion capture that you're referring to, that you would have for the movies, you really again have these specific key points that you mark, and you have special cameras, and you also have a special lighting that gets reflected from these markers. That's making it easy and also super reliable to track them on like a millimeter scale for the movements. Now for this 4D scanner, there's a different concept, because we do not want to track specific markers, but you really want a full 3D scan of the body. So you want to have the finest possible resolution that you can get. So there are no markers whatsoever, but there are many, many cameras again, and there are speckle patterns projected onto the person. And then you try to reconstruct from those speckle patterns on a very high timely scale. I think it should be more than 50 hertz, I think even up to 100. Please don't go further into details than that. And you can really, like, for every single one of these frames, you get a full 3D scan of the body, which means that you can also like track tissue movement and stuff like that. And this is something that is not yet seen that much in movies or also in computer games, right? The people still look very, very static. So the arms are very static, even though you have clothes on them. And the graphics people are, of course, trying to add some wrinkles to the clothing, but it's still a very, very hard topic.
Interesting.
And having this resolution helps you to go further into details on that.
Yeah. Okay. I think that makes sense. I'm glad I asked, because my mental model is a little bit different than I would have expected. So thank you for the clarification on that. So tell me a little bit about what the research actually is in your own words.
Okay. So for this specific thing that we've been looking into, for this fitting to single images, that was a lot about finding out how to go from a few sparse key points, and now we're talking again the plain original key points as they are classically used, So detecting those in an image as reliably as possible, and then going from there using an optimization to a full 3D representation of the person in the image. And that means still we have this body model that is being built from many of those 4D scans that I was talking about. So you're trying to build a statistical model over all the possible bodies that you could observe of humans. And then fitting this body to the few sparse key points that you have in an image. And it is a little bit like magic, because you can't really solve the problem right. It's impossible because you have this perspective distortion, so you can't really match. There are ambiguities. And the only thing you can really do is to build a prior on the pose that a person usually can assume, and then try to match it as good as possible. And then the cool thing is that you then not only get a 3D representation of the pose of the person, but you really also try to estimate the body parameters of the person. So you can get an estimate of how big or small a person is, how long the arms are, for example. And by using the body model, you also can guarantee that it's somewhat plausible, right? We usually don't get any monsters that are really strange people, but it stays somewhat realistic. So that's a nice point.
Cool. So I think I'm going to share my screen real quick, and I have the paper pulled up. Are you able to see my screen?
Yes.
Okay. Cool. And so this is kind of a little bit, these are kind of the first images that are shown in the paper of, and this would be great, I think, for the audience watching this, of like, okay, you have a person on a horseback and a jockey, and then your guys' model of trying to estimate what that pose might look like. And then that third photo is the actual kind of model on its own, right?
That's right. Couldn't have said it better.
Cool. And then a soccer player, and I think there's some more photos. Not to scroll through all your hard work here, more images. Yes, another example of someone walking. And so the intention, and I think you articulated this, is to say, hey, how do we take a single photo of a person in any particular situation and then figure out what the 3D model might be behind that action? Is that
exactly?
Okay, cool. And so here's, actually, I'm going to try to zoom in here on, so these are a little bit more, take us through some of these kind of more unusual positions here that we're looking at.
Yep. And you see for example, in the third image, there are actually two people in the image, and the key point estimation, maybe you can even zoom in a little bit more onto the third one. And you see that the key point estimation, because it's forced to talk about one person in the image, it scatters the point across both, because for every single point it uses the most plausible one, but on its own it does not have a global body model, so it fails to really capture the 2D pose. And you can see that on the right hand side you still get a 3D person that still is plausible in a way. Of course, the pose of the person is then screwed up. Right. I mean, it's just that can be done to match the 2D evidence. But by still having to stick to a proper body model, you get something reasonable. It's not totally far out. I mean, it's not the truth. Unfortunately, the 2D estimator screwed that up for us, but you still get something reasonable.
Yeah, that's I think of all the different challenges with this, right? And you have two guys standing, side by side, both wearing white t-shirts, kind of dark pants, and all of a sudden you kind of have an issue. So that's interesting. There were some more photos that I wanted to pull up, but one of the things that in the paper that I thought was really interesting was also this idea of, and I think this is the section right here, of, you guys talked about kind of making shapes of the body that could create a realistic representation that didn't. And I was picturing when I was reading it, kind of like two arms, and I think you called it capsules. Can you talk a little bit about capsules and what that meant to you?
Mm-hmm. Sure. So the capsules are here coming into play when it again is about the staying to realistic bodies and realistic shapes. The problem is that still the body model that we're using is a very abstract and only graphical representation. It's not physical. So that especially means that it could happen that the arm, for example, is going through the body. There is nothing that prevents this from happening, just in a graphics world, leaving physics aside. And the capsules that are depicted here are one take to prevent this from happening. It would, of course, be possible to use a full-blown physics engine to try to prevent this, but that would make the optimization super, super slow. So the capsules are an abstraction away from the really fine-grained, detailed version of the body to still remain fast during the optimization, but also prevent this interpenetration, what it's usually called in graphics. And in this case, we add one term to the optimization that increases in energy. And usually in the optimization, you always try to minimize something. In this case, we're minimizing the energy. And this energy increases as soon as two capsules are going through each other. And so this is trying to prevent exactly this from happening. And
cool.
Yeah.
That's a really cool concept. It's a great way. It seems like a really great way of kind of using a simple approach to protect yourself against kind of these unusual arrangements. And you said like you could do the physics model, which is obviously very costly, but it seems like a really great workaround.
Yeah, I mean, this is still like I think the optimization that's currently going on, it's still on the order of several seconds per image, so like 20 seconds for one image. So of course, like efficiency is one of the critical points to keep in mind to remain feasible on a larger scale. And even like 20 seconds may be prohibitive, but of course, like you can push this down a lot more if you want it.
So another thing I read, and I think this was, and I'd love for you to kind of take us through so that I don't misrepresent this, but you talked about deep cut and kind of a CNN-based method to kind of predict bottom up, and then you kind of did something top down that was generative. Like, could you talk a little bit about what that actually means? Kind of, could you explain that in your own words?
Sure. So the deep cut model that we use there is just a model to get those 2D key points. So we're not limited to deep cut. I found it to be a very, very good model that's also super fast, also for training. So to put a little bit of advertisement in here with all the concurrent models out there, but it could be any other, right? So you could use any other one to get to those 2D key points. And this is going from the 2D image to the key points. So it's trying to discriminate what is already there to find out exactly where the positions of the key points are. And then, as you put it nicely, there is the other way around. And once we have the key points, we generate something, go to the generative side and go try to make the body model that we generate match as good as possible the evidence that we had from the discriminative part. So it's this very nice cycle. You bring together both worlds. And what is very good about it is that the generative model in that case is very restricted. We know that if we generate something from this generative model, it is plausible. This is again the plausibility issue that I've been talking about before. So using this cycle is exactly what gives us like nice properties and nice guarantees in that case. And of course, you can think of like using both of the sides by themselves, right? You can try to do this all in a discriminative way, or you can do it all in generative way, and then you lose advantages for both of them. If you do it in a totally discriminative way, you're probably a lot faster, but you do not have this like model in your thinking for that we use for the generation that gives you guarantees. On the other hand, if you do it on the full generative side, then you're even a lot slower because you have to explore all the possible bodies that you can generate to track down the right one that will match. So you're completely unguided.
Right.
So then again, you lose something else. So yeah, it's trying to bring together the two positive sides.
So it's looking at a photo. It's trying to make some assessments of saying, okay, we have evidence that there's maybe a joint here. There's a certain
Yeah.
other thing here.
Yeah.
We think that it's looking like this. It then takes that information and starts generating a model that would then is against kind of, and I believe you said in the paper that you have this really big data set of kind of how humans move. And, I'm thinking of my elbows. Hopefully they don't move opposite jointed often, but in general, they should bend inward, and I would crouch in kind of the fetal position. And so then it generates models based off of the evidence to kind of say, hey, this is a realistic-ish pose that's probably close to what this person in the photo is doing.
Exactly. So
Cool.
So that was the CMU mocap data set. In that case, that just contains many motion capture recordings of people. So just to cover the general pose space that a person would take. And it's just, I mean, this is also strictly speaking not necessary, but it helps you to narrow down the search space to somewhat reasonable areas and to disambiguate some of those parts where you say, there's many possibilities how this photo or how this configuration could have been produced, but actually realistic are only these, and then we stay to those ones.
Yeah, interesting. Yeah, cool. Thank you for explaining that. What was the most challenging part of all this work?
All the details. Perseverance, and I have to say that yeah, again, like the first two authors, like Federica and Andrew, did a great job for narrowing down this energy function that is used in the final paper that we've been talking about most of the time, to really represent the most reasonable parts of the pose space that you could converge to, and that involved a lot of experimentation to get it just right, to fix the problems that can occur. For example, this elbow bending that you were talking about, that you get an extra term there, that you make all these things fit together, that you weigh all the terms in the energy function right, because this is something that you cannot derive. There is no way. You have to optimize it properly, and this also involves a lot of like human help for getting things right. And yeah,
cool. And there's a bunch of applications that are coming to my mind, but what are some of the most interesting or exciting potential applications of this general technology when you think of it?
So there are really, for luck, quite some. So we didn't have one specific application in mind for this project. But when you think of it, for example, VR right now, right? It's a huge hype. And I love the idea. I still don't see it quite there where it's really fun for everyday use and for every possible customer. But I see huge potential there. And for sure, you could use this technology to, on the one hand, transport a person into VR, because you can actually properly find out more about its 3D configuration. And I think for interaction in the virtual space, it could be really interesting. But then also for getting the movements of a person and transporting it kind of to some other place, right? Just for the sake of recording or whatever, because you can actually compress it quite nicely. You do not have to have another 3D scanner that you place around the person, but really just record it. So I think that could be very nice. And then also robotics. Like if we were to get this fast enough, right? It would be very nice for interaction with robots or with any computer system. Because it does not only tell you about the 2D position, but really about the body extent in 3D. So you could shake a hand, right, with a robot like that, or I don't know, interact in any possible way. And robots include autonomous cars, right? They're nothing but robots. So I think for autonomous cars, they have other ways to currently approach this, which are already a lot faster and under guarantees, very, very, very fine-grained and detailed. But yeah, I mean, maybe for other ways to interact with the cars or for the pedestrians, who knows what's going to happen. But yeah, I think that we could do quite some nice things.
Yeah, it's what jumps to my mind when I hear you kind of talk through some of these things is I think that ability to be able to take a single photo or a single feed or a single moment in time essentially and be able to extrapolate into something else in virtual reality, augmented reality, gaming environments, simulation environments, I think it has some interesting applications. You know, I don't know why my mind's going there. Maybe it's just the state of the world at the moment, but I'm picturing like a security camera being able to, you know, it's filming a public place and being able to take that one feed image and being able to understand maybe the context of what an entire crowd might be doing, to have a better sense of, is there anything dangerous going on in that situation? It seems like there's all sorts of different value adds in order to be able to take this, you know, relatively flat piece of information, which is funny to say about a photo, but and turn it into something so much richer and more immersive, and all the way to, you know, recreating a family moment. Maybe, you know, maybe the first step is recreating where the humans are at, and then maybe replicating the setting is really easy, and the next thing you know, you can hop into any photo you've ever taken, and it's a VR setting of, you know, you're at Disney World with your family in the 90s, right? Like that's going probably way too many steps down the road, but I think it's really cool. Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show. What are you working on next? What are you excited about?
So I think on the short term, there are some things to tackle that are pretty obvious. For example, getting it fast, right? Or getting things more detailed, like adding adjectives to this, right? Positive adjectives, like whatever you can think of, right? Make it better, make it more detailed. I think there's still a lot to do and to be explored, because it was just a first take on it basically, and there is still a lot of potential left. But then I think like what I'd be really excited about, and this is then of course a little more general speaking than out of the scope of just this project. But what I'm really, really curious about is how we will be interacting with machines like on the longer run. And this is what I was saying. Like, of course, this enables machines to get a better estimate of what you're up to, what your 3D body is currently doing. So it's helping certainly, and then there are for sure many, many more steps required. Question is where this will go in the end. I mean, will we have AIs that are mostly focusing on understanding us and helping us and like interacting with us like very, very closely and just trying to push this? Or will we be working towards AIs that are autonomous and that do not have to see us basically all the time? So this will be it could be very different approaches on how things are developing. And I'd be really curious to see in which direction we are going. And if we're interacting with machines so closely on a like everyday basis, then of course like this technology will have to evolve a lot more. But it should be super cool. Like I'm really curious and happy and trying to find out what will happen.
Yeah, that's an interesting. When I was thinking of the applications, my mind was going very kind of like human digging into advancing a human cause. But when I think about that of kind of machine vision of saying, okay, I see a person in front of me, and like, what does that mean? And even thinking of all the different poses that person may go into, if the machine's handling me in a physical way, it would probably be good for it to know that my elbow shouldn't bend the other way in case it thinks, oh, I'm going to pick this human up and its elbow is going to fold in the wrong way. Like I should know that, which is really something that I hadn't considered, putting kind of the lens on of the machine. That's pretty cool. Yeah.
Yeah. And it's not self-explanatory, right?
Right.
I mean, we should teach the right things before we go in this direction.
Yeah.
Yeah.
That's cool. Well, hey, I really appreciate you joining the show. Thank you for taking us through everything. Thank you.
Um, thank you again. It was a great pleasure.
All right, thanks. Bye.
Bye.